Testing. Testing mic, testing mic. Awesome. We got a question. Let me pause that just for a second. And let's go to... boom, boom, boom. So first thing I want to do is make sure there is a... Okay, so I'm gonna answer this. Let me just write something really quick. Boom. And let's go here. So what I want to do, get my iPads to stream to my computer, and I'm also going to make a quick note on our Canvas board so any other students who have this question can see what we said or what we talked about in my office. Come on, come on, come on. And let's do that. Because I probably could vocalize it to you, but we might want to have some pictures for people or some words that people can see and some stuff that's going on. Okay, let's see. Oh, I gotta deal with that. Okay. Stream might drop for just a second. It'll be back up, or it should just reconnect immediately, but... From a usability standpoint, I need to get a little bit quicker on some of these things. Most students are going to be like, oh, it's so terrible, all this technology. And start broadcast. Okay, great. So now I want to go back to this. Let's move this over here so you can see my screen. Let's go over to here. Go back down here. Okay, so we have a, put it on Canvas. Check the time. It is hour 25. Okay, so what we want to do is let's look up just for a second. What's a good example? Probably that one. So we're going to look up CL2 mass spec and make sure I can see if the student has any questions as we're going along. There. And there we go. Okay. So we go here to chlorine, and we look at the data over here, and the when we look up the let's just even see if I can get a wiki page for chlorine to come up for me. No, we're gonna have to actually spell it. Okay, so see if we can find something about isotopes here. Okay, great. So. And again, I think in one of the classes I probably did a better job of talking about this, but the natural abundant, percent abundant, so percent abundance, this mic's over here a bit more. So for percent abundance, this has to do with on Earth if we have all the chlorine on Earth, what percentage is chlorine 35 and what percentage is chlorine 37? So we're taking all of the chlorines, 35s and 37s, putting them all together, and then going through, and we're finding that for percent abundance, and really it should be on Earth, our chlorine should add up to 100, right? All of my chlorines that are on Earth, I should be able to tell you this mass or this mass. Either they weigh 35 or they weigh 37 for every single one of them, if that makes up all the chlorine on Earth. And so it should add up to 100. And so the percent abundance of chlorine on Earth is about 75% of it is Cl35, and about 25% of it is Cl this. So this should add up to 100. Because you're describing all the chlorine on Earth, that's the percentage. But when we look at mass spectrum, when we look at kind of data that we get from the mass spectrometer, the mass spectrum, there's this concept over here where we have relative intensity. And all relative intensity is actually doing... So let's pause here. Before we go forward, any questions is on percent abundance. In my opinion, and maybe I'm making this up, but I'm pretty sure percent abundance is for, the planet you're on. The solar system has made this planet, the whatever, sun you have, whatever meteors have hit you, wherever you are in the galaxy, your planet has a certain abundance of certain isotopes. And so for Earth, this is what we found on Earth is 75% of them are 35, 25% of them are 37. Okay, great. So then we have to figure out this next part, right? What the heck is relative intensity? So when we look at relative intensity, what I want you to see is that the 100 is set to whatever the highest peak is. So in this case, let's write that out. So intensity percent, which is that what they say? They call it relative intensity, but we'll say the same thing. So I'll write both of them. So we have relative intensity, or as you called it, intensity percent. That's probably the more accurate way to talk about it, but I get what you're saying. What this does is it basically says whatever hits the detector the most, set it to 100. And so if we take our example of, really, I'm shooting these things, I can't just shoot chlorine through. It's a halogen. Can you even see my periodic table? Maybe you can. A little bit, yeah. So it's like, because it's a halogen, because it's on that side of the periodic table, as we talk about bonding theory, we're going to find that these things want to be bonded together. So typically, we see them bonded together. We can have chlorine 35, 37. We can have chlorine 37, chlorine 35. We can have chlorine 35, chlorine 35. We can have chlorine 37, chlorine 37. And on top of all of this, when it goes through the detector, right, the bang, bang, bang from class, that bang, bang, bang of trying to make it charged sometimes breaks bonds. And so we also can have some chlorine 35 that goes through, and some chlorine 37 that goes through. Now, again, all of these are cations. All of these are cations of some form that the detector is counting. So it's counting. depending on how many chlorines we put through here, the y-axis could be all sorts of different numbers. The y-axis, if I shot, 20 million chlorine atoms through my detector, I'd have 20 million on my y-axis that I'd have to, well, I'd count up to some crazy amount of numbers. Or if I only shoot 10 of these chlorine diatomic atoms through the mass spec, then my y-axis would only be going up to 10. So how do we portray this information when sometimes we're sending through the detector 10 molecules and sometimes we're sending millions through the detector? So instead what we do is we do this relative percentage. So in what we're seeing on here, it seems that the chlorine 35 and the chlorine 35, right, if I shoot through 1,000 of them or whatever, or let's say I shoot, let's just make an easy number. It's got to be a weird number though. So like if I shoot 150 of these through the detector, you're going to find that the most of the 150 hit the 70 detector. So most of these 150, rather than having a y-axis that counts out of the 150, how many times did I hit the detector, I'm just going to say, well, whatever hit the detector most, in this case, right, let me point it out. On this case, we have 70 is at the top. That has been set to 100. Whatever data processing I'm using is just saying take this and set it equal to 100%. And so now when we look at the relative intensity of these, we need to realize that percent, or not realize, but we want to come to terms with percent abundance is saying just out of all of them, what is the ratio of isotope to isotope? So percent abundance is done in this column, or in this side of the spectrum here for diatomic atoms, and we can approximate it still. We can say, well, it's about 80-ish, and then this one is about, it's getting a little bit closer to, what, if 30 is right about there, it's a little bit below 30. So we have these, let me kind of do this math just for a second. So what I'm trying to say, or wait, I have an iPad. So, right, if I'm approximating it, it's like, well, the chlorine 35's relative intensity is, let's just ballpark it at about 83%, and chlorine 37's relative intensity is getting close to 30, but it's a little bit below 30. So let's just estimate, I don't know, about 25, 26 maybe, 20, let's just say 27%. And so what we can do then is we can add these two numbers together, part of why I chose 7 and 3, right? When I add these two together, overall I get about 110, and so I can think 27 out of 110, 83 out of 110. This returns me now to the percent abundance. But I'm not necessarily going to be able to read off of a relative intensity chart and say, oh, 83% of them are 35, 27% of them are 37. That's not what you want to do. You kind of add up what their intensities are, and one of them might be 100, but often it's not. Often it's going to be below the 100, and you can count those relative intensities. So they are, we call it normalizing, or the math people would say normalizing our, however many we set through, we're setting that to 100, and then just taking a percentage ratio. We're taking a percentage of the population that we're defining as 100. Well, if a population less than that came through, because it's not the thing we're setting to 100, we're always setting our top limit to 100. Now, anything that comes in underneath should have less than that. Less molecules should be hitting the detector at 72. Less molecules are hitting the detector at 74. That's the least. But I can still approximate based off of, if this means that 100 of them were this, then 11 of them were this. And you can still use that to help you kind of do some of the math, do some of the predicting of what are the different types of isotopes we could see. But I think the primary focus is to say, for this question in particular, and I'll kind of maybe slightly end it here and see if we can add questions to it. But I want to leave it to say that the long and short of it is that percent abundance is it should add up to 100%, and it will represent on all of Earth how much of an isotope is this, how much of an isotope is this, and it has to add up to 100%. But the relative intensity, or the intensity percent that we're talking about here, these numbers I circled in red, and their estimations from the graph, they don't add up to 100. They add up to more than 100. But by adding these two intensities together, I can still go in and say, by knowing the two intensities together and then saying, well, this intensity, this over the total of those two, this intensity over that, it's going to get us to what should be very, very close to. This should be about 25%, and this should be about 75%. And so that's where we then come back to percent abundance. So it's to again, or to make it even more shorter, but kind of coming back to what I was saying earlier in the discussion, it's to normalize it so that it doesn't matter if you shot 20 moles worth of the atom through, 1 mole of the atom through. We can use relative intensity to make all of these y-axes easy to read. The y-axis is easy to comprehend. So I hope that helps a little bit, but it is, you're normalizing it to whatever hit the detector most, and then setting that equal to 100%. So like, let's even do just for fun. You might, if you're good, just let me know, but I'll just do like an example of, let's say I have some diatomic, let's make the CP atom that we're sending through, and we find that CP atom has a mass of 50, and that's like, I don't know, there, and then we have this one here that's 52, and then we can have, actually, you know what, instead of doing a fake example, because then I'll have to do the math quickly in my head, which maybe I could do, but let's just go back to the classic bromine and bromine. When we look at that one, what we find is there is a, let's look at it. And we saw it in class, but you understood? Great. Awesome. I'll just keep talking just for a second for anybody who watches it afterward. Okay. So blah, 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 blah. And then we got this one, and this one. And so this is set to 100. And so let's just say then that, let's say this is actually 50 hits. We're saying that, let's put that at 100, or what's a better color? Maybe yellow. Let's put that at 100. And so we're going to say 100 is equal to 50. And so you would then realize that the stuff that's coming in at about 50, let's do a different color for this. Right, but the stuff that's coming in at 50, the hits is 25 hits. And so 50 equals 25 hits of the detector. This hits the detector. And this is it normalized. And what's the other one? It's like 10%. And so here at 10%, and it's a little bit more than 10%, but at 10%, that would be 5 hits. 5 times the detector gets hit. So, cool. Thank you so much for that question, and we will put, oh boy. That was 142. so ordinary. You got Hello, hello, hello. Okay. And is my iPad even still streaming? Oh, maybe it is. It is. Okay, great. And let's see what the question is. I know in class we talked about mass spectroscopy is what I'm going to say. And maybe that's even the wrong word. I think it's the right word. Mass spec, we'll just say, so everybody's right. I know in class we talked about mass spec, but could you explain the purpose of the magnet in the system? Yes, I can. So let's even see if we got anything. There's even some really cool videos on this. I really should post a video, well, because I don't want to make a video on that. Let's even see if we can find the blah, 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 blah. Yep. I will say that my understanding is that the magnet affects things that are charged differently, where they hit the detector at different places. And so the magnet's job is to, well, before I answer this, let me put it in the office hour. Okay. And this is at 2 hours and 1 minute. So the purpose of the beam, or the purpose of the magnet, is to bend the beam. So when I look at this, we have the thing that gets it into gas form, then we're propelling it, then we're hitting it with the electron that's making it charged, then it goes through a beam focuser, so we have a beam. The answer to your question is, could you explain the purpose of the magnet? The magnet takes the beam and breaks it up based on mass and charge. And so the mass and the charge, because it's charged and because they have different masses, the magnet takes the beam and turns it into different beams. What is this a great example of? All right, it's kind of the same thing that's happening here. We have this, except instead of it being a magnet, it's a prism in this case, where we can put a white beam through a glass prism, and then the prism splits apart the wavelengths. The magnet is doing the same thing for us, or at least for our pay grade. What we need to know for the exam is the magnet's job is to take the beam and separate it into separate beams that have different masses, and they are curved because they're charged. Look at that. I actually might have answered a question and not monologued for like 10 minutes. Does that help a little bit? Think of it as a prism, I think, and maybe this isn't a great analogy, but it's doing this. It's taking, instead of it being light, it's taking all of the masses. When it gets charged and is affected by a magnet, the beams split off into the different, we see masses and charges. The prism example is you see the different parts of white light. Same kind of thing. We're not using a prism, we're using a magnet because we have things that are charged and they go different places based on their mass. For further stuff, and I think I might get a little bit copy strike for showing it, but there was a good mass spec video. If I can find it again. No, I don't like this one as much. This one I think is a cool one. No, it's still not it. But again, for our pay grade, let me know if that helps. There was like a company that made a video. I remember watching that one and liking that one a lot. A company who sells mass specs made a video on YouTube that I saw, but I don't see it anymore. This one is probably a good one, but does that help you a little bit? Or does that evoke another question in you? We need to think of it as or I would say at its simplest, it's a prism, but instead of separating light, the magnet helps us separate masses and charges. Awesome. Awesome, awesome, awesome. Okay, awesome, awesome, awesome. So I'm going to add this to the, what was this? About 2 hours and 56 minutes. What is this? This is question 1D on worksheet 3. I think it's worksheet 3. Yes, it is. Okay. And let's get my iPad up. Nice. Let's get a fresh window up if we need some. Oh, well, we want this. And we want this. Yums. Okay. All right, about to show all this stuff. So the basically we had a student come in and say, "Can you help go over the last thing you did in class?" And so let's make sure I can get my iPad a little bit easier to see. I think I need you to come to the forefront. Okay. So let's get back to what it is. So basically, estimate the ratio for the masses of 158 to 160 to 162. We are trying to understand why is 160 the highest, right? That's, or at least to me, that's one thing that comes out to me as like something we might be curious about. So it's like, and in some ways, this is actually a Discord question too that I'm going to be answering for chlorine. But 160 is the highest peak, and then it looks like 158 and 162 are half of the highest peak. And in class, what may have confused students a little bit, just because there's a lot coming at you guys, but we are doing claim evidence reasoning whenever we run across these explain questions, right? In this, it says explain why this ratio is observed. Typically, we're going to want to have you do some claim evidence reasoning. In my opinion, if it does appear on an exam, we should be very clear that we want you to write a claim evidence reasoning based answer. But a lot of the worksheets will have some claim evidence reasoning in these explain questions. And so I'm going to completely write. So when we see explain, when we need to explain this, right? This is what I'm seeing. I'm seeing that 160 is the highest peak. Seeing 158 is about half of that. 162 is about half of that. Can I explain this? How do I do it? I'm going to explain it using a claim that is backed by evidence and that I have a decent reasoning for. So that's the three things. What I wanted to hopefully say in class is that start here, then go here, then make the claim. All right? Don't say the earth is round without having any evidence or any reasoning. Look at the stars, do the trigonometry, start doing some reasoning about how through trigonometry, this is what we would say. And okay, cool, good question. So they're also asking us, what the heck are with the other two bars on the left? Those two bars are bromine broken apart. So when bromine, if I look at my periodic table, I see that bromine itself should weigh, apparently on average, 79, but it doesn't. It weighs, actually by mass spec, sorry, I shouldn't say this. Bromine on the periodic table is close to 80. It's about 79.9. So we might think, well, doesn't bromine weigh 80? No, it doesn't actually. Half of bromines weigh 79. The other half of bromines weigh 81. And so when you pick up a bunch of bromine on Earth and you start picking through the bromine you picked up on Earth, imagine you're able to atomically. We can do it with mass spec, but just go on a vacation with me. Let's say we become really, really small, and then we we pick apart, right, how many bromines are 81, how many are 79, we find it's 50-50. And so the average weight we get is 80. But what you're seeing, and so those were broken apart, but bromine itself, because it's a halogen, and once we get into some bonding theory, this will make a little bit more sense, but bromine itself actually wants to bond with something else. So the 160 numbers, 158, 160, and 162, are two bromines bonded together. Bromines by themselves should weigh around 80, and they do. They weigh 79 and 81. So I hope that helps with that question. The student question was, are the two bars near 80 also bromine? They are bromine. They're one bromine. The other bars are two bromines. And notice your learning objective is just diatomic, just two atoms and how they're combined together. And yeah, we don't need to go into crazy in depth for mass spec for unknown compounds. But anyways, let's keep looking at this. So to kind of bring me back to what I was saying, again, we need to have claim, evidence, and reasoning. I say start here. I say start by looking at the evidence. The evidence is the mass spectrum, and then we can develop some reasoning off of it. So the evidence that I can gather, right, and evidence should be some measure thing, something we've measured, right? It should, whether it's an amount, a charge, a kilojoule, or whatever, but it should be measured. And so our evidence here is that the P table, so let's do green. So one piece of thing we have is P table says on average bromine is equal to 79.9 AMUs. I don't know if that's helpful, but it's something. It's a piece of evidence. I'm pulling from a reference. Number two, though, we have that about two isotopes exist for bromine, and I want to make a real big note here. Right, look to the left of the mass spectrum, right? Over here, because there's two lines, the detector is being hit by two things that weigh different amounts. The detector is getting hit by something that weighs 79, and the detector is getting hit by something that weighs 81. So that's how that's my evidence, is that I'm looking at this detector, and the detector is saying that the amount of 79 and 81 is equal in count. And so I tried to stress as best as I could today in class that class 3 is about amounts of things and weights of things. How high the red line goes up on the y-axis, how high that red line goes up is telling me an amount, how many times the detector was hit. Where it is on the x-axis, the lines that go further to the right, that's how much mass is being detected, how many times the mass that's detected. And so we're counting how many times these masses are detected. And I can say that the amount of times it hits 79 and the amount of times it hits 81 is equal to each other. So when we break apart a bromine connected to a bromine, right, just as a quick side note, right, when I put bromine in bromine and I grab an electron, here we'll make it comical-ish, it's horrible, but, right, I've got my electron gun, and so I'm shooting these electrons that have a lot of high energy, and so this thing's like, oh my gosh, I've got so much energy that's coming out here, and it actually breaks this bond. And so we break apart, right, the electron breaks this apart, and possibly the things that were bonding it together, these are actually electrons that bond the bromine together. It's possible that these are the electrons that are ejected. It's possible that 2 go on to 1 bromine doesn't get it. I don't know, right? I don't know. Maybe someone knows. I don't know. If we know when a bond is broken, if it's the electrons that are being ionized or something else. I don't know. I'm not, and we don't need to know necessarily. But what we need to know is that the electron gun sometimes breaks apart the bromine. And so sometimes we get it counting at 79, we get a hit on the detector. And sometimes we get another one that, well, the other bromine was 79, so we get another count on the bromine. But other times we'll have the bromine, right, let me get these out of the way. So let's pull that off to the side. But we also could have a bromine like 81 connected to a bromine 79. And so again, I take my electron gun and, oops. So I take my electron, shoot it again, breaks this, boom, hits this, breaks this bond, boom, boom, boom. This is just smacking into this thing. And now breaks apart. And so the detector will count these times that we break it up. Okay, so yeah, exactly. Yep, you got it. Okay, I think I got it. Is that why it's 0.5 times 0.5 for 161, right? Let's see. The 2 bars. Okay, wait, I think I get it. That is why it is 0.5 times 0.5 for 161, right? I don't like, the one thing I don't like is just the number 161. I'm wondering if you meet 160. You're getting close to it. You are definitely talking about the right numbers. We just want to talk about them in the right way. So let's keep kind of moving along and just keep building off of this evidence. So we know the periodic table tells us something. We know that the left part of the mass spectrum is telling me what are my what are my isotopes and how many of each isotope is present. In bromine, it's nice. They're fairly equal to one another. This is not always the case, but in this one, they are equal to one another. And we can then also look at, we have evidence for the 158, 160, and 162. So that's the last piece of evidence we need or the last piece of evidence I think we can pull. Are all these pieces of evidence helpful? Not necessarily, but it's worth thinking about what can we start pulling information about. So, okay, the third piece of the evidence is that about 160 is most common weight, and this goes to your comment. 160 is most common weight of a non-broken but ionized. Right, we had to ionize it or else the magnet wouldn't feel it. 160 is the most common weight of non-broken but ionized Br2, or we can think about it as a Br connected to a Br. 158 and 162 are less common and only are less common and about half of whatever amount is hitting here. I don't love how I've explained this, but I'm just trying to say that this height over here, I'm noticing this peak is about half of the largest peak. So the largest peak we set to 100, and this peak is being counted to be about half of whatever this peak counts to, and this one is counting to about half of what this one counts to. Why is it this way? Why does it look 1 to 2 to 1? And so maybe at this point we just say we got to make the claim Well, so I'll leave that there as we've done the evidence. This is where I recommend us starting. Periodic tables, average atomic mass, sometimes helpful, sometimes not. There's a good discussion on Discord going on about it. 2 isotopes exist for bromine that we looked at the left side. And then I should add a note really quick that this is for, now we're looking at the right side. And again, thank goodness we're only doing diatomic stuff. That makes our life a lot easier. So right side of the spectrum is going to tell us about them together. That's all the information we can pull. So now let's start doing some reasoning. And our reasoning here is mostly math. So our reasoning is basically, oops. Oh, shoot. All right, so we can say that the high, oh, is it going to put it into words? Oh my gosh, that's so cool. The high peak, I don't like it though too much. The high peak at 160 comes from the most likely combo of 79 and 81. Let's think about all the possible combinations of bromine in spot A and bromine in spot B. We're kind of making a table here. So one thing is that bromine A can be 79 and bromine B can be 79. Another one is that bromine A could actually be 81 and bromine B could be 81. And so we can add these up. 79 plus 79 is 158. 81 plus 81 is 162. And the likelihood of it being 79 is 50%. The likelihood of it being 81 is 50%. Again, where am I getting this? From here, from my review of the left side of the spectrum has me saying that, well, they're equal to one another. And so if you have 79 or 81, it's a coin flip here. I've added that, like, these two maybe both go up to 10, right? If both of these abundances go up to 10, then I'm saying 20. First line is 10 out of 20. That's 50%. Second line is 10 out of 20, all the isotopes. So again, half. And so we can then say that, well, the likelihood of these two is 50% times 50%. And so let's kind of do that off to the side. So we'll say 50% times 50% equals 25%. So we know this could happen 25% of the time. Same thing for this one. This one could happen 25% of the time. And then the last one basically says, well, of course, it could be 8179. And then where I got destroyed on my first chemistry exam was it can also be 79 and 81. Right? It doesn't have to be whatever technically the first part of the diatomic. It doesn't have to always be 81. It can sometimes be 79 followed by 81. Same thing again, these are both percentages, but these weights add up to the same number. They add up to 160. And so we have to add up the percentages, right? This is again 25%. This is again 25%. And let me be clear. I'm saying it's 50% times 50%. That's where that 25 is coming from. But I do it again for this one. 50% times 50% is 21. And I add these two together, though, because I could say it could be either one of these. And so these things happen 25% of the time. These things happen 25% of the time. This combination gives the same mass and happens 50% of the time because I add them up together. And so now I'm starting to see the ratio should be, if I set 25 equal to 1, then 50 is equal to 2, and I have a 1 to 2 to 1 relationship. Those lines, about one line, these are now two of those one lines, and that's why the ratio is observed. I'm using math and probability, and so I would say then the last thing I would do is just go down and make the claim. Now that I've looked at all the data, I've said, okay, evidence told me what the isotopes are, and what is their relative heights, their counts, their base unit counts to one another, and what is their okay, wait. I have another question after this one. How does the mass spec tell the relative abundance of pairs 159, 160, or 161? Because when they break apart, you can only really tell if they came from a pair of 159, 160, or 161. I also have another question. Does the sensor of the mass spec tell us the mass by reading the location it got hit, by reading the speed of the atom hitting them, or both? That's even, well, I'm sure there's a video. Well, let's go one thing at a time. So, and we'll put it in the timestamps too. So, let me hopefully think I finished this one for the most part. Let's finish by just writing the claim. The claim that we could see is that, well, what are they asking us to explain? Explain what the ratio is. Or no, we need to estimate the ratio. We're going to claim the ratio is, you could say 1 to 2 to 1 for 158 to 160 to 162. Or I'd be okay with 25 to 50 to 25. I'd still, oh, you can't see this. Let's put that over there. All right, so there's my claim. The claim is just, it's my answer, and all my work now has explained it above. So I hope that helps a little bit. Now I can go back to making sure I understand the student's question. I have a question after this one about how the mass spec tells the relative abundance of pairs of 159, 160, 165. So when they break apart, you can't really tell if they came from a pair of 159, 160. So you may need to rephrase your question, but what I think well, let me say this. I should look into this a little bit more, but I would say the likelihood of breaking a 159 is, you're not as likely to break a 159. You're more likely to break apart a 160, and you're less likely to break apart a 162. Why? Because we know from relative intensity that typically the thing that's going to be hit with electrons the most is 160. So you'll break apart the 160 and get an 81 and a 79 that will hit your detector. You'll bing 81 and 79. But sometimes if you get the 279s that come through, the likelihood of breaking a 158 and a 162 is less than breaking a 160. And so it doesn't matter where it came from. It doesn't matter if my 79 that hit the detector came from a bromine that was both 79 and 79 versus a 79 that came from a 79 and an 81 bonded together. It doesn't matter where it came from, because this is why we ionize it. We know that as I'm consistently trying to ionize these bromines, I will more often than not ionize a 160. The other half, or the other, I guess, 50% of the time I'll ionize a 160, 25% of the time I'll ionize a 158 and a 162, but it will still give me the same distribution of 50-50, 79 and 81. So I hope that helps a little bit with that. And then I want to, yeah, I should do another timestamp for this, because that, I think, ends that topic. Because now we're talking about mass spec stuff. Like, what do we need to know? Because there's a learning objective about mass spec. About, I think there is. Is there not anymore? No way. What? No. Did I waste time? No. Oh, dang. Dang. They took away that learning objective. Well, okay. Good news, bad news. You guys learned more than other classes, but we actually don't have to understand how a mass spec works. So let me answer this a second. So this went from here to, go here to 320. and then we'll say 3 hour 21 minute. Because I am in the right. Fall 2025. Oh, that was my bad. They've edited, I think, the learning objectives, right? Unless it wasn't an earlier one. No, it doesn't. Okay, well, we don't have to know. But to at least attempt to answer your question, I'll say I am not... so let me just answer this question too. So first, I want you to realize, or I want to say, what did I call this? Yeah, great. So I want to just say that for mass spec, what time was it about? Yeah, for mass spec, I'm looking at the learning objectives. We actually don't need to know how it works. So I apologize about that. I still think it's pretty cool where they're getting it from. And I think it's important in some ways because you have no idea what M/Z is until you understand how a mass spectrometer works. So we'll say it was worth it in class. But the good news is I don't think we have to answer your question. The next question is, does the sensor of the mass spec tell us mass by reading the location it got hit or by reading the speed of the atom hitting them or both? My safe answer will be I would not be surprised if different companies have different sensors, but what we can say is that the sensor is somehow, and let me pull up this picture. We know that the sensor itself, what the beam comes into it, and I explained this like a prism. So in a prism, we have a beam that comes in, and then the beam goes through a prism and separates into different wavelengths. Think instead for us that the mass spectrometer has a line of things that weigh different. So bromine 79, bromine 81 in this line. We don't put it through a prism. We put it through a magnet. When it goes through a magnet and it's charged, we do have to bang an electron out of its atom. Once we get an electron out of it, then the magnet can affect it. And then the magnet separates the weights like a prism, and visually we see it here, separates them where lower masses curve more, other masses curve less. And I'm not 100% sure what a Faraday collector is, but there's some sensor that notices that the prism or the magnet is separating a beam into different masses that I'm fairly confident the magnet can pull on a lighter mass, not as much on a heavier mass, not as much on a heavier mass. But could it be different for other instruments? Yes, this is a sector type mass analyzer. There may be other ways that we have an analyzer. There may be other ways we have sensors that are measuring it. But again, not a learning objective, so we shouldn't be tested on it, but I hope that sates your curiosity. Okay, so mass spec doesn't tell people the relative abundance of pairs of bromines, but tells people the relative abundance of bromine isotopes. I actually think it does. I think it does the other one as well. It does say that, like, if I have, I would say it does. I would say the mass spec tells us because of the right side of the spectrum. The right side of the spectrum is saying, like, over here, it's saying that most, right, let's just, let's, although this isn't, like, hyper accurate, I think it'll help explain a little bit. Let's just say that the total count of things in here is a count of 50. There's 50 things that are in these lines, right? If I could count how many times the detector was hit, across these three lines, the detector was hit 50 times. And so the highest peak of this thing, if I set it to be like the highest or whatever of the peak that we were hitting at, and then these peaks are both half of whatever this peak is, I can say to myself, well, I guess that if I set 25 as, this is getting confusing. If I say instead of, so over here this is percent, intensity. But what if I actually do counts? I would have 20, or not 25, I'd have about, let's say about 12, and up here's about 25. 25 of them hit the 160, 12 of them hit the 158, another 12 of them hit the 162, so 12 plus 25 plus 12 is approximately equal to our 50 that we started with. And so we can, but some broke, so you can't tell which pairs the broken ones came from. Yes, I love that you keep coming back to this, but you can still argue that you're likely to break this more often. You're less likely to break this, and you break this. So when we are breaking apart these things, we are bringing down this level at twice the, it's twice as likely to bring down a count there, less likely to bring down a count there, less likely to bring a count down there. So I do agree with you that it does feel weird that the ones that broke, I'm not accounting for their counting, but I can say that it is more likely that I broke a 160 twice amount of the time I broke a 160 that I broke a 158 than I broke a 162. I was twice as likely to break a 160 than I was to break a 158 or a 162. So if I flip a coin enough times, I get to 50%. If I break a bunch of these off, it's like, sure, I had out of the, right, like overall I had, and this is where, forgive the math because the math won't be hyper accurate, but let's say overall it was 60, and that means that 10 broke. So if 10 broke over here, we know that 5 of them are reading at 79 and 5 of them are reading at 81. But we broke off of these peaks, the 79s and the 81s. This breaking off of these peaks over here broke equally off of each peak. So each peak, if they didn't break, the peaks would go, this peak would go up by about 5, this peak might go up by 3, and this peak might go up by about 2. So the breaking happens statistically at a certain amount because we vaporized it. So if we didn't break them, then my 10 would go back into those lines, 5 would go into the middle line, 3 would go into one line, 2 would go into the other line, approximately. Again, we would need like moles worth, like millions and millions worth to get accuracy, like flipping a coin millions and millions of times, because it wouldn't be perfect, right? But I'm using simple numbers that I can understand. So great. Awesome. Well, I'm going to then say we'll call that a office hour for tonight. I'm going to answer that last question on Discord, and then I will be back to helping with problems tomorrow. So thank you guys for stopping by. Thank you so much, and I will see you.